Problem number 7, calculate the factorial. An easy problem, but something new here. Given a non-negative integer n, we want to find its factorial. Okay, yeah. Method 1, method 2. Iterative, recursive. Yeah. Method 1, iterative. That's simple. Yeah. By the definition of factorial. You just use a for loop. Yeah. But here, when we start, here, we need this. N factorial equals 1. Do you know this? N factorial equals 1, not 0. Okay? N factorial equals 1. That's the assumption. Yeah. That is the assumption. Yeah. But it looks like, because we expect a 0 something should be 0, usually. But here, it's special. Here, it is special. Here, if we assume 0 factorial equals 0, we will get trouble. We will get a lot of trouble. Yeah. 0 factorial, if we assume equals 1, everything works perfect. Yeah. Yeah, I will explain that later. Later, I will explain why 0 factorial equals 1. Yeah. All right, yeah, so here, it's hard to see. Yeah. But later, when we have some formula, we will see it. All right, yeah, okay, yeah. Implementation is simple, right? Yeah, one for loop, yeah. Everybody can do that easily. Yeah. But method 2, now we want to move the recursive method. Yeah. And this is probably the easiest recursive method. Yeah. Okay. All right. Idea, yeah. Here we want to apply some general problem-solving approach here. Okay, so what's that? The general problem-solving approach. Divide and conquer. This is a very important problem-solving approach. And our module 4 will be divide and conquer topic. Yeah, whole module 4 devoted to divide and conquer topic. Yeah. But here we use it. Yeah. Divide and conquer. Yeah. So let's take a look at the basic idea of that divide and conquer. Yeah. The first simple observation. The problem is easier. It's a general property. A computing problem is easier when the size is smaller. The smaller, the easier. Typically, okay? Typically, yeah. Yeah. All right. Number 2, when you work on a problem of the current size, yeah. So here, this is the divide and conquer way. Divide and conquer, all right? Yeah. When you work on a problem of the current size, you have a current size you need to deal with. Assume that the problem of a smaller size has been solved. Yeah. Yeah. You assume that has been solved because you can start from the problem with smaller sizes. Yeah. So you make that assumption, then you can do recursion. And at the same time, it follows divide and conquer idea. Okay? Yeah. Number 3, yeah. Fix the gap through a recurrence relation. Yeah. Because the smaller size and the current size, there is a gap, right? Yeah. There is some gap between current size and a smaller size. How to fix that gap? You need to do some work. Fix the gap. Then you can get the problem solved. So that is the typical divide and conquer approach implemented using the recursive algorithms. Yeah. So that's our theoretical part. Now, let us work on it. Factorial. So we use factorial to help us understand this procedure. Yeah. First, we assign a function to it. F factorial, f of n equals that n factorial. Yeah. Because if we have a function, then we can develop that recursive formula. Okay? Yeah, recursive formula. Yeah. How to develop recursive formula? Yeah. From expression here, we do the observation, try to find some property. Try to use the 3 steps here to develop that recursive formula. All right, the first critical step, look at this line. So what's the meaning of this line? Cut off one element from the string, okay? Cut off one. Why you cut off one? Simple, reduce the problem size. Cut off the last n, that means we just calculate the factorial of n minus 1. How about that? The problem size becomes smaller, and we can assume n minus 1 factorial is known. Yeah? This point number 2, assume the problem of smaller size has been solved. So f of n minus 1 is given. You can assume that. Why you can assume that? Because recurrence will help us, make sure that assumption is okay by recurrence. If no recurrence is allowed, you cannot assume. Okay? If recurrence is not allowed in your programming language, you cannot assume that it is known. Only when recurrence is allowed, you can make that assumption. Okay? That's the point. Yeah. After that, if it is known, you just do another multiplication to fix the gap, right? The step number 3, we need to fix the gap. So do multiplication. One multiplication will help us fix the gap. The gap between f of n and f of n minus 1 is one multiplication with n and f of n minus 1. That's simple. Okay? So this is the recursive formula. So we discover that. Yeah, that's the key step. Yeah. This formula, the key step, recursive algorithm, divide and conquer. How do you reduce the problem size? Divide and conquer. Yeah. And you have this formula, write a recursive function. Solve it. Yeah. All right? Yeah. Here. We assume n greater than 0. Yeah. Now, we go back to our previous question. How to see n factorial equals 1? Why? It makes sense. Yeah. Yeah. So you have to convince people. Yeah. Here, let's do one thing. We have to convince people n factorial equals 1. All right, so let's do the convincing work here. Let us rewrite this formula. We know this formula is correct. Can we write f of n minus 1 equals f of n over n? Yeah, division by n, both sides. So let us rewrite that formula. All right. After that, can we plug in n equals 1? N equals 1. How about that? If you plug in n equals 1, 1 minus 1, that's 0, right? F of 0 equals f of 1 over 1. F of 1 factorial is 1, right? 1 over 1 equals 1. What is f of 0? F of 0 is 0 factorial, right? Yeah. Based on our function definition, f of 0 is the 0 factorial. F of 0 here is 1. So that's the way how you convince people. 0 factorial equals 1. All right? Yeah, not magic. Yeah. We use solid, rigorous math to get the conclusion. Okay? All right. Okay, yeah. So the conclusion, yeah. So this, here I talk about the general recursive algorithm. So it is an interesting way to solve problems. Yeah. Useful, interesting, and powerful. Okay? Yeah. All right. So next topic, power of recursive algorithms. This time, I want to show you how powerful it is. The meaning of power here, yeah, let me say another time, a relatively complicated problem. Problem is pretty hard. And you can use recursion to solve it in a relatively easy way. That's the power. Yeah. And another point, if you do not use the recursion to solve it, it is extremely hard. That's the point I want to convey in this 8.2 topic. Yeah. Our problem number 8, Tower of Hanoi. Yeah. So the puzzle problem, I think you're familiar with that. Let me quickly go through, but this time we use the recursion, divide and conquer, solve it. Okay, all right. Yeah, so here, let me just use a 3-disk version. Our goal, we want to solve n-disk version. Okay, not 3-disk version. 3-disk version, that's the typical puzzle that people do in the, real world. Yeah, real world for kids, challenging the kids if they can solve 3-disk puzzle problem for the Tower of Hanoi. Yeah. Non-trivial, you need to do some work, yeah, but solution pretty smart. Yeah. All right. The rules first. Yeah. Rule number 1, only one disk can be moved at a time. Yeah, every time just only move one disk. Rule number 1, easy. Rule number 2, a disk cannot be placed on top of a smaller disk. Yeah. So when you place a disk on top of another disk, check the size. If the disk already there has larger size than one of the current disk, okay? Otherwise you cannot place there. Yeah. Second important rule. Yeah. Rule number 3, all disks must be stored on a peg except while being moved. Yeah. Let me explain the last sentence. Last rule, also important. All disks must be stored on a peg. Yeah, we have 3 pegs, okay? Yeah. So when you move, after you finish your move, your disk must be located in one of the 3 pegs. Yeah. All right? It means you cannot put a disk on table temporarily. Yeah. Otherwise, too easy. Right? If you're allowed to put some of disk, spread on the table or floor, then it's too easy. So here, in order to make the problem more challenging, we need 3rd rule. Yeah, you have to one of the 3 pegs. Yeah, no other places you can use. Yeah. Yeah. So with these 3 rules, let us try to solve it, do the analysis. Yeah. Our goal, n disks. Very hard, right? Yeah. Our goal, solving this problem with n disks. Extremely difficult, right? Yeah. But our strategy, working on a problem with relatively smaller size first. So this is the first step towards that goal. Oh, yeah. Anything wrong? Yeah, I thought you point out someone. Yeah, trying to get in. Yeah, Jude, because Jude is missing. Yeah. All right. Start with. Let us start with 1 or 2. Too easy. 1, one move, you make it. Yeah. But how about 2? 2 also pretty easy, right? Yeah. So I think you can do it in your mind easily, right? Yeah. The thinking here. When we solve this is a critical step. When we solve the problem of size 3, the current problem, we can assume that we have already solved the problem of size 2. Yeah. We have solved the problem of size 2. Why you can assume? Here, one reason we can assume, because we can solve it easily, right? Yeah, we know we can solve it easily, but we cannot assume, right? If someone tries to challenge you, why you can assume? You just do it. Okay? Show them, yeah, I can solve it easily. Yeah. So it's okay, we can do it this way. Yeah. All right. That is the recursion. You can see, that is the recursion. Yeah. You already have the solution of problem size 2. Now fix the gap, right? There is a gap. Problem size 3, problem size 2, there is a gap between them. Then you need to fix it. Then you have the whole solution. Okay? All right, so now for n equals 3, non-trivial. Yeah. So let us try this case to get some experience. Yeah? We need to work on it. We need to get some experience. We need to understand this problem a little better. Yeah. So we need to do some work. Okay? Yeah. So next, let's do it. So experiment. Moving 3 disks based on that 3 rules. Yeah, we cannot violate those 3 rules. All right. Now, diagram. Step 0, before we make any move, the original setup. Okay? Yeah, it's like that. So step 0, okay? Initialization. Yeah. Then step 1, we make our first move. Top disk, we move it to peg 3. Yeah, that's easy. Yeah, nothing to worry. Yeah, the first time. All right. Step 2, second disk, we can only place it on the middle disk, not the right peg. Yeah, middle peg, not right. Yeah, because you violate the rule, right? So you can only place in the middle peg. All right. Yeah. Then after that, you cannot move, right? Look, the bottom, the largest disk, you cannot move anywhere, right? Yeah. But you can move the smallest disk back to the middle peg. Yeah. You can move it back. Try to make empty peg for largest disk. Yeah. You need to make some room for the largest disk. Yeah. So here you can see after you make that move, we solve the problem of size 2, P of 2. That means the problem of size 2, we just move those two disks to a different peg, following the rules. So that's why you can make assumption. Step number 4, we move the bottom disk to the empty peg. Yeah, easy. Then after that, we need to move these two disks another time back to the last peg. Yeah. So that is another P2 problem. So we need to solve the P2 problem twice. First time solve P2 problem once, second time solve P2 problem another time. Okay? Yeah. Step number 1, how to solve P2? Yeah, another time, move the smallest disk to the first peg, yeah, and second disk to the last peg, yeah. Last move smallest disk to the destination peg. That's all the whole procedure of the puzzle solution. Okay? Yeah. Now, but after we go through these 7 steps, complete procedure, yeah, we want to find the rule, we want to find some properties to help us to get a general solution. That's the goal, the general solution. Okay? Yeah. All right. How do we generalize the solution to n disks? Okay? Yeah. Here, so let us solve the general case recursively. We have the experience from the 3-disk problem. Now we extend it to the n-disk version and solve it. Yeah. Here, without using recursion, you can think about it is very hard to solve the general case. Yeah. People can try, but extremely hard. Yeah. All right. Recursion method. In the recursion method, we use the problem size reduction approach to help us implement recursion method. Okay? Yeah. To solve a problem of size n, this time, yeah, we make our assumption, we can easily reduce it to a problem of size n minus 1. Yeah, smaller size, we can assume we have the solution. Okay? We have the solution. Yeah, all right. Let me just use the diagrams, part of it. Yeah. This time, I want to show you how to modify it to make it work for size n problem. Okay? All right, so when we start, here we give 3 names for the 3 pegs. From, the first one, from, coming from, yeah. Temporary, the middle one, temporary peg, to, yeah, the destination, to peg, yeah. We give 3 pegs, 3 names that we can refer these 3 pegs. Yeah. And we imagine there are n disks here, not 3. We imagine it 3. Yeah. And we need to solve P of n. Yeah. Size n. Yeah. All right. Now, okay. Yeah. So when we work on it, yeah, because it's too complicated. Yeah. But we can assume because here we assume we can solve problem size n minus 1. Can we assume we just apply n minus 1 solution to move n minus 1 disk to a different peg, different destination peg? This temp peg is used as the destination for n minus 1 pegs. Disks, yeah, not pegs, disks. Yeah. Okay? Yeah, because we assume we can solve it by recursion. Here, just by recursion, you can solve it. Okay? Yeah. All right. After that, yeah, because you have it, we already have this step. So next step, we move the largest disk to that destination, 2-peg. Yeah, that's easy. Okay? Yeah. All right. After that, we need to move the n-1 disks back to the destination peg by solving another p of n-1. See? Yeah. Another time. Yeah. And to write the code, yeah, this is the way to write the code. Okay? This is a C function. Yeah. All right. Yeah. Then when the recursion, yeah, the number of disks, 3 pegs. Okay? Yeah. So 3 integer variables, 1, 2, 3. All right? Yeah. So then we call this function move disk recursively. Yeah. And we assume n-1 problem can be solved in this recursive function, but we need to change, when we solve it, the order of the pegs should be changed, right? From destination 2, that's the second, temporary third peg variable parameter, but here the destination is peg, all right? The temporary 2-peg is used as the temporary peg, the third one. Yeah. All right, after that, when we move the bottom disk, how do you do the simulate disk moving? Print out a message. Print out a message. That's the simulation of disk move. Yeah. Move a disk from peg number to peg, another peg number, end it. All right? So that's the disk move operation. Then another recursive function call, but we need to change the 3 peg variable parameters in different order. Starting peg, temporary peg, that is used as a starting peg. Destination 2-peg. Yeah, that's our real final destination, 2-peg. And from peg is used as the temporary one. And we run that solution another time. See? Yeah. This short function, how short it is. Very short, right? Yeah. Very short. So this short function can solve a difficult problem, right? Yeah. This problem looks pretty difficult for n-disk problem. That's the power of the recursive algorithm. That's the power. A difficult problem can be solved simple way, short code, by recursion. How powerful it is. Think about that. All right? Yeah. All right. Yes. Okay. Next topic. 8.3. Simple recurrence relation. In this one, we need to calculate the disk moves. How many disk moves for an n-disk puzzle problem? N-disk this time. Yeah. Do the calculation. Okay. Yeah. Tower of Hanoi efficiency analysis. Efficiency, basic operation. What is the basic operation? Disk move. One disk move, we treat it as a disk operation, as a basic operation. Yeah. So we count the number of basic operations. Yeah. All right, move a disk from one peg to another. Yeah. Yeah. We don't care which peg to which peg. Just one disk move. Yeah. Define the count function C of n. Yeah. We need a function name to derive recurrence relation. Yeah, recurrence relation. What is the recurrence relation for C of n? C of n. number of disk moves for the problem of size n. Yeah, that's the most important step, recurrence relation. If you can find it, yes, the solution is not far away. Yeah. All right, that is the formula. C of n, the disk moves for n disk problem. Remember, you need to solve the n-1 disk problem twice, right? Yeah, based on our procedure, twice, so you need 2 times C of n-1. And the bottom disk, you move the bottom disk in the middle, right? In the middle, so plus 1. Yeah. So that is our simple recurrence relation. Simple, so simple, right? Yeah. That is simple. Yeah. So the next question, how to solve this recurrence relation? How to solve? It looks not easy, yeah, because this is a recursive function. It's not our regular function. Yeah, it's not our regular function. Yeah. Yeah. So we should solve it in a different way. So here the solution, you need to do some smart work here. Smart work. Okay, yeah. So you really need to find some special properties. Yeah. All right, initial condition, C of 1 equals 1. 1 disk move. Oh, yeah. All right, so now let us solve the recurrence relation. Yeah. What kind of math operations? Yeah. Transform the formula. Yeah, we need to change the form. If we just have this form, we cannot see how to solve it. In this kind of situation, yeah, if we work on the original formula, this is the original formula, it's hard to see how to solve it. In this kind of situation, usually try to change the form of the formula to make it more friendly for us to find the special properties. Yeah. Here, how to change, solve the recurrence relation. How to change it? Yeah. How to transform the formula. Yeah. Explore the similarity in structure. Explore similarity, left hand, right hand side, left hand side C of n function, right hand side C of n minus 1 function. Now you look at the structure, the plus 1, right hand side, left hand side no plus 1. So if you compare the structure, left hand side, right hand side, they are different. The question, can we explore similarity? We want to change the form such that both sides, they have the similar structure. That's the consideration. That's the tricky part. So that's usually, people, not easy to get it. Yeah. All right. So let us try to make the plus 1 structure. How about that? More specifically, the function, the recursive function, plus 1. We want to see that plus 1 structure. Similarity, both sides. Left hand, no plus 1. All right. Can we add 1 to the left hand side to get that plus 1? Yeah. Because we want to make both sides, they have the similar structure. Left hand side we have plus 1, right hand side also we have plus 1. Here plus 2, but after we factorize 2, common factor out, we have this C of n minus 1 function plus 1. Now you can see both plus 1 structure. How about that? Similar, right? That's the way we explore similarities, both sides. Then we can take advantage of the similarity. So you may want to ask why it helps, right? Why this kind of similarity structure helps us solve this problem. Yeah, the answer is easy. Because we have the similar structure, we can introduce a new function, only one function, to represent these two similar structures easily. That is, let us introduce the d function. D of n equals c of n plus 1. Then this parenthesis part just d of n minus 1. See? You can see. We introduce a new function and we can make our original recurrence relation simpler, right? This one simpler because the plus 1 is gone. See? After you introduce a new function, that plus 1 thing is gone. How about that? Yeah. Okay, yeah. Initial value, yeah. Because d of n equals c of n plus 1, c of 1 equals 1. 1 plus 1 is 2. So d of 1 equals 2. Yeah, our initial. Now we need to solve a new recurrence relation. How to solve it? Yeah. We know it's easier than that one. Plus 1 is gone. Yeah, but we need to solve it. Yeah. So let us try to do it. Yeah. All right. Let us try to apply this formula, but this time we change n to n minus 1. So the right hand side, n minus 2. Yes. So we apply that recurrence relation another time. Then after simplification, 2 squared times d times n minus 2. Yeah, you replace d of n minus 1 by 2 times d of n minus 2. So you have 2 squared, 2 times that 2, 2 squared times d of n minus 2. Yeah. And so on. So you can keep doing that, but how do we keep track of everything in the middle, right? Using invariant idea. Remember, invariant idea, we do the string matching problem, invariant idea. Here, because when we go to next step we are moving. When we are moving, which quantity is invariant? Never changes. When we move, there is one special quantity, never changes. Yeah. Try to find it. Okay? Try to find it. Yeah. All right. We move it all the way to the last one. You can see exponent number 2 plus the number inside the parenthesis n minus 2. 2 plus n minus 2 equals n. So 1 here, okay? 2 to the first plus n minus 1 equals also n. You can see those two numbers adding together, that's the invariant. Never changes. So you can go all the way. When you do the work in the middle, that number, this number inside parenthesis at exponent position, adding together, always equal to n. That's the invariant. All right. So the last one, because last one we want to have d of 1, the base case, d of 1. So the exponent number should be n minus 1. n minus 1 plus this one should be n. So we can figure out the exponent of the power of 2 for the last step. Otherwise, we may get lost, right? What is that exponent number? Because it's hard to keep track of all the way to the end, right? Nobody can do the work from beginning to end. But we observe this key property, so that key property can help us to figure out what is the exact expression at the end. Invariant idea. How about that? Okay? Yeah. So that's the So the last step, d of n equals 2 to the n. Go back to the c function. Yeah, c function d of n minus 1. So the c of n equals 2 to the n minus 1. So we solve the problem. We solve this recurrence relation. Yeah, so here you can see. Yeah. And try to understand the invariant idea. Yeah. The second time we use it today. Yeah. Later we have many other places we can use this idea. Okay, yeah. All right, so that is this topic. Yeah, yeah. We have 10-something minutes. Yeah. Yeah. If you do not have question, I want to start a new topic. Yeah, because we have to use all the possible time. Yeah. All right. So the next, yeah, this one, yeah, I think. Yeah, is that? Yeah, yeah, good, yeah, that is this one. Yeah, that's the one. Part B, variable size reduction and Fibonacci numbers. Yeah, this part B, yeah. Let's start. The first part, variable size reduction. Yeah. From its name, you can see reduce the problem size. But when we do the reduction, each time the size part could be different. So it's not a constant. For the factorial problem, that's constant. Every time we reduce by 1, the size reduction is constant 1. Yeah. And not necessary always constant 1. Yeah. So we have freedom to do the size reductions. So B.1 reduce the problem size by half. Yeah. 1/2 size reduction. Okay. All right. Problem number 9. Count binary bits. Yes. So this problem, yeah. Now, count binary bits given an integer n. Given an integer n. Yeah, positive decimal integer n. Okay, yeah. Find the number of binary digits. Yeah, that's bits. Okay, binary digits in its binary representation. Okay, yeah. So it's a simple problem. Yeah. Yeah. But the solution is not that simple. The solution, we need to use a lot of math. A lot of math in the solution. Okay, yeah. So let us do analysis. First, let us review binary representation. In the discrete math, you learn this topic, binary representation. Yeah. So here, let me review. Given n, we can use bits. Yeah, all these B0, B1, the bits in the binary representation of n. So you can see we use the base 2 as the base to represent the binary expression. Yeah, that's the standard binary representation form. Okay, yeah. All right. And the most significant bit, B sub s, cannot be 0. Yeah. Must be 1. Yeah, otherwise, you don't need that bit. Okay? So the last bit, the most significant bit must be s, must be non-zero. That is 1. Yeah. All right. Yeah. Then the answer, yeah, because the answer, the number of binary digits, that's the bits, number of bits if we count here, s plus 1. If you know s, but we don't know s, okay? If you know that s, then the answer is s plus 1. Yeah. All right. So the question becomes how to find that s. How to find that s? That's the question. Okay? Yeah. Yeah. All right. From n, given n, we need to find that s. Okay? So that's the problem. Yeah. Inside, we want to try to find some property, critical property. So inside, yeah. Use a transformation to change the structure. Yeah. Just in our previous problem, the puzzle problem, Tower of Hanoi, we did that. So this time we use the same way, yeah, but we need to do some different transformation. Yeah. Division operation. How do you do division? Yeah, because when you calculate the binary, the bits, you need to do division, right? You need to do division by 2. Okay? Division, base 2. That by division by 2 operation, right? Yeah. So look at that. The standard expression, let us do division by 2 both sides. You can see, yeah. Yeah, remainder, yeah. So other than the first term, each one is a multiple of 2, right? Yeah, each one multiple of 2. But the first one, not multiple, may not be. The first one could be 0, that's multiple of 2. But if it is 1, not multiple of 2. Yeah. Yeah. But we take the floor function, left-hand side, division by 2. If we take the floor function, the first one is gone. The first one, no matter what, no matter it is 0 or 1, after we take the floor function, the fractional part is gone, removed. Yeah. Remaining, we reduce the exponent number by 1 for each term. Okay? Yeah, b1, b2 times 2 to the first, and so on. Yeah. So reduce exponent number for each term by 1. Okay? Yeah. Let us make observation. Yeah. All right. The least significant bit is removed. After that division, least significant bit is gone, disappear. Okay? From the expression, you cannot see the least significant bit. 1 bit is gone, right? 1 bit is gone. The number of bits is reduced by 1, right? If you compare these 2 expressions, the number of bits used in these 2 expressions, difference is 1, reduced by 1. Okay, so that property. Yeah. The problem size is reduced by half. This is the problem size. Okay? Now the problem size becomes n over 2. Half size, half of the size. Okay, yeah, yeah. So we can get a recurrence relation. Based on the observation there, we can derive recurrence relation. Okay, all right. So this is recurrence relation. The function, binary recurrence being rec of n. Yeah. The number of bits in our binary representation is this function. Now, we reduce the size n over 2 floor function because we cannot use n over 2. It's another integer. Right? So we have to use the floor function. Then we call the same function to get the number of bits here, but we know the difference is 1. So we need to fix the gap. Adding by 1, we fix the gap. Okay? Yeah. So we have the whole recurrence relation. Okay? The whole recurrence relation. Yeah. The question is how to solve it. Not challenging, right? How to solve this recurrence relation? Think about that. Non-trivial, right? Yeah. Comparing with our previous recurrence relation, this one much harder. Much harder. Especially, you have a floor function there, right? Floor function, so this not easy to handle. How to handle that floor function, right? Think about that, okay? All right. Yeah, the base value, base case value, yeah, 1. Okay? How to solve this recurrence relation? Yeah. All right. Yes. Okay. Yeah. All right. If we write a program, we can do a recursive function implementation. That easy, right? Yeah. If we write the code to calculate that function value, it's easy. We can do it in this way. Yeah. But here, we're not satisfied with this solution. Although you can calculate, but that is, you need to run this program. Run this program to do the calculation. Yeah. A better way, we want to have a better way. The better way is we really want to find a formula for this function. Formula. That will be more useful than this version. This version, you can treat it as a solution, computational solution, but we want a mathematical solution here. If possible. Many times it is impossible to get a mathematical solution, but here it's possible. It is possible. But we need to do a lot of math work. So that's why I say this problem relies on a lot of math work. Okay? But we cannot do it today. Only 5 minutes left. Yeah. So I want to leave the math detailed solution next time. Yeah. Next time. Yeah. 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 Next time we start here, solution. Yeah. Yeah, so one student asked me about a programming project. Yeah, I'll make sure today. Yeah, so I post that description and give you 3 weeks. So today is Wednesday, right? Yeah, today is Wednesday. So I set a deadline 3 weeks from today, Wednesday, midnight as the deadline. Yeah. Okay? Yeah. So although, when we get there, so when you have any special requirements, so I try to make sure, to help you, yeah. But we need to start the work, yeah. So I'll post the description, yeah. So then I will explain some of the, details in the description, yeah. All right, so let us stop here today, yeah. So we, another thing I like to, because I still have 4 minutes. So let me say a few words related to what do we need to do this week. Yeah. Quiz number 2. We finished module 2. So we should do one quiz for module 2. Yeah. Quiz number 2, yeah. So let me tell you the time I post. I cannot wait till the weekend. I don't want to wait till the weekend. So I want to post it as soon as possible. Yeah. But let's do this. Today I post the programming project description. So I only do that. Yeah. So tomorrow I will post the quiz number 2. Thursday, quiz number 2. Yeah. So then give you, approximately 1 week, usually a little more than 1 week. Yeah, it's okay. Yeah. Hope you can do better. So that's quiz number 2. Yeah. After that, this weekend, homework number 1. So we are in the middle of Module 3. Yeah, we just get started. Yeah. But when I make the homework assignment number 1, because I want to cover a little more in Module 3. Yeah. So this weekend I can post, but I cannot post all the questions. Yeah. So I may post, let's say 15 out of 25 questions. One assignment, 25 questions. But we have Module 1, Module 2, so I plan to use 15 questions in Module 1 and 2. Module 3, yeah, I leave the last 10 questions, Module 3. Yeah. After we complete, so I put that module, remaining 10 questions. Yeah, so that's the plan for this week. So you can see, we will have a lot of work. Yeah. For short semester, so we will have a lot of work. Okay, yeah. All right, yeah, that's it.